Thanks again for coming tonight. Don't have TV, so we've got the live web stream going, and I'll start here. Thanks again for coming to Wednesday Night at the Lab. I'm Tom Zinnan. I work here at the UW-Madison Biotechnology Center. I also work for the Division of Extension and Wisconsin 4-H, and on behalf of those folks and our other co-organizers, which is Public Television, the Wisconsin Alumni Association, and the UW-Madison Science Alliance. So thanks again for coming to Wednesday Night at the Lab. We do this every Wednesday night 50 times a year. Tonight, it's my pleasure to introduce to you my colleague from Extension, Maureen Muldoon. She's with the Wisconsin Geological and Natural History Survey, which is part of Extension. She was born in Milwaukee and went to high school at St. Mary's Academy, which she tells me no longer exists because they merged with St. Thomas More Academy. St. Thomas More of Man for All Seasons fame. I don't have a movie made for my namesake. High school. And then she went to Washington University in St. Louis, where she studied Earth and Planetary Sciences. She came here to UW-Madison to get her master's degree in glacial geology and groundwater. And she worked for the Wisconsin Geological and Natural History Survey for 11 years. And the last few years of that time, she was getting her PhD here, again at UW-Madison, working on fluid flow in carbonate rocks. Then she spent 27 years with UW. 21, sorry. 1 and 7 are very similar. 21 years with UW Oshkosh, and she's on leave from UW Oshkosh, now back working with the survey. She's going to be talking with us about why are Wisconsin's karst aquifers so susceptible to groundwater contamination. Would you please join me in welcoming Maureen Muldoon to Wednesday Night at the Lab.
Well, thank you for coming out on a nice cold night. Sometimes it's easy to covey on the couch, but you actually came out, so thank you. So it's sort of a broad topic, and I'm going to be bouncing around the state, but how many people have actually heard the word karst before? Oh, bunches. Okay, good. Okay, so here's a quick summary of what we're going to talk about. Karst aquifers vulnerable to contamination. You got to know the bedrock geology. Got to know the water cycle. Got to know soils. And you got to know land use. Okay, so we're really going to focus on these first three, just talking about what is the geology of the state and where do we have karst aquifers. A little bit about the water cycle, just to think about groundwater and groundwater basics and how does water get into the ground. And then soils. You don't always think much about soils, but we actually expect them to do a lot for us in terms of cleaning up water. And right here, that's rock. So that if you don't have much, that's sort of a big hint about why things are vulnerable. Right? Okay. And then land use, it really depends. Like, are we doing agriculture? Are we urban? Do we have forests? What do we have on top of that karst landscape? All of those things are going to come into play with vulnerability. So being a former UW Oshkosh professor, I like outlines because then the students kind of know where you're going, right? So we're going to start with geology and karst. Bedrock geology, what is karst and where do we have it in Wisconsin? And then we'll move on to these other things. Okay, so this is a very simplified picture of Wisconsin's geology from the Roadside Geology of Wisconsin book, which if you like geology, that's a great book to have while you're driving around the state. But basically in the northern part of the state, we have very old rocks, primarily igneous and metamorphic rocks. And then we have this big, thick package of sedimentary rocks on top. So this big blobby thing down here we call the Precambrian, those old igneous and metamorphic rocks. And then we have these big, thick packages of rocks that were laid down in oceans quite a while ago. So we're going to start, you have this, well, this is just kind of a generalized one, right, where you've got just by ages, Silurian, Ordovician, Cambrian. We're going to look in a little more detail in the next picture about what those rock types are like. And this figure actually has lots of blues on it, which the projector doesn't seem to like very much. So here's those very old, very colorful rocks up in northern Wisconsin. And then here's the best place to kind of see that this would be as if we took a knife and went from the west side of the state over to the east side of the state and sort of sliced into it, like slicing into a cake, and looking at those different layers. This is the Michigan Basin. All the rocks, they look flat when you drive around, but they actually dip very gently into the Michigan Basin. And so on top, we have this little dab of Devonian. Then we're going to the older and older rocks. We've got the Silurian dolomite that we're going to talk about a lot. right? And then underneath it, we have the Maquoketa Shale, this little pink thing here. I used to live on top of the Sinope Dolomite here. And then we have the St. Peter Sandstone, and then we have more dolomite. And these rock layers sort of wrap around over here. All of these kind of pinky, or the bluey and the greeny ones, the Ordovician age ones. The Silurian is really just limited over there in the eastern half of the state. Okay, so those are your rocks. And I mentioned that you had to have carbonate rocks. So carbonate rocks are things like limestone and dolomite. And when you think about where that forms now, how many people ever been, think white sand beaches? So think like Bahama Banks, right? Those kind of places. Off of Belize, you've got a barrier reef. Warm, tropical, shallow waters. That's where you make limestone and dolomite. Not very much like it is outside today. But that's where these rocks formed, in those kind of settings, when Wisconsin was down by the equator like hundreds of millions of years ago. Okay, so you've got your carbonate rocks. Now what is karst? This is a picture from Door County. And I hope you're noticing these nice linear features here. Right? We're going to talk about, karst has just a straight up definition. It's a type of topography or landscape that's formed by dissolving rocks. Pretty much what it comes down to. So it's not the karst. It's not like the sinkhole or the fracture or the cave. It's the whole landscape. Because you've got to think about how water is moving through that landscape and dissolving stuff. So limestone and dolostone are dissolvable. Gypsum's dissolvable, right? And what kind of things do we get? We get sinkholes, we get caves, and we get a lot of underground drainage because there's like big cracks and holes in the ground that let the water in. And there is a huge range of karst. Okay, how many people have ever seen the tower karst in China? Just those little spires, right? I've seen pictures too. Someday, when I'm retired. Right? So what those are is just imagine a whole bunch of sinkholes, and that's all that's left is those little spires. The sinkhole plain near Mammoth Cave, right? All these little holes where the water soaks in and then convenes and makes Mammoth Cave. That's karst. Door County, Wisconsin, where you have fractures that are a little bit dissolved and a little bit bigger, that's karst. I call it like baby karst. It's not like Mammoth Cave. We don't have huge caves underground there. So there's this huge spectrum of landscapes that are all karst, right? And there's a lot of it, okay? About 20% of the land area in the U.S. and about 40% of the area east of the Mississippi. So this is a landscape that's pretty common in the eastern half of the U.S. So where do we have it in Wisconsin? Go back to thinking about where you had carbonate rocks. This is where we have the Silurian dolomite, and this is where we have those Ordovician age carbonates. These two colors, the kind of orangey brown one here, is 0 to 50 feet of sediment on top of that rock, and the tanny colors are greater than 50 feet. So all of these kind of browny orangey areas are areas that we would consider to be susceptible to karst. This is a really nice picture from Protect the Water You Drink tips for homeowners in Door County. This is very much what the landscape in northeastern Wisconsin looks like. There are a network of vertical fractures. Sometimes those are expressed in the vegetation, and you can sort of see them as you did in that previous slide. And then the layers of the rock are also fractures that help move water. And when we do have things like this, you always think like, well, why does a sinkhole suddenly open? It's been forming for a while underground, and just eventually the rock above it and the soil above it collapse into it, and then suddenly it gets expressed at the ground surface. So that's why sinkholes, you might hear about a sinkhole opening up. The hole underneath has been there for a long time. It just suddenly busts through at the ground surface. Okay, so this is very much what the northeastern Wisconsin karst looks like. In the southwest, it looks a little different, and we're going to spend a little time on that more near the end. This is a slide I got from Tony Runkle, who's with the Minnesota Geological Survey. And here you see the kind of typical things, sinkholes and fracture traces and caves. But this is your dolomite, and then you have other rock types underneath it. And here you pretty much have all dolomite, lots of dolomite. So there's a little bit differences in terms of how these karst systems behave, and we'll get to that more near the end of the talk. Okay, so here's just some pictures of southwest Wisconsin karst, a sinkhole, right? This is a road cut along Highway 151. If you ever take 151 down to Iowa, you see tons of little karst features. Well, if you're driving like me, looking at the road cuts as you're driving, you'll see tons of karst features, like vertical features, little round things, little things filled with red clay, right? That's a weathering product of the dolomite. You see all those things along the highway. And then this, I completely stole this from the Cave of the Mounds website, big caves underground. I figured it's okay if I acknowledge it. Snagged it off their website. Okay, so we're going to focus first on northeastern Wisconsin karst because I started working at the survey in 1987. So I've been working on this aquifer for more than 30 years. Much better at understanding the groundwater flow in this system. So you see the Silurian dolomite here, right? It wraps around the Michigan Basin, up through the Bruce Peninsula in Canada, comes around. It's what makes Niagara Falls, right? Same rock layers, and then it comes around down through here, Ohio and Illinois. In the southern part of Wisconsin, it's kind of buried a little bit, but you really see it from Dorr down through about Horicon. As you're driving up, you see the ledge rock, right, where there's that big cliff of dolomite. That's what we're going to be talking about for the next little bit here. This is a picture from a quarry in Door County, Wisconsin, up near Sturgeon Bay. And you see the different dolomite layers. Sometimes they're white, sometimes they're kind of tannish. But there are these bedding plane fractures that you can see pretty clearly. You can also see these vertical fractures. Now, you might think, oh, that's just because they blasted it to get the quarry there. But no, they're persistent, and they're throughout that aquifer. So the fracture network is a big deal with the karst because that's what's moving your water. Okay, so this is a slide of an alfalfa field across from an old research site. And what you see is over the bedding plane, over the vertical fractures, the alfalfa is kind of happy, right? Because that fracture is a little dissolved and a little dirt washed in there. Alfalfa tends to be kind of deeply taprooted. And so over the fractures, the alfalfa is a little happier and healthier. Over the blocks, not so much, right? But the fractures are everywhere. They're like every 30, 40 feet apart. And here's a different field. I mean, they don't stop right there, right? It's not like all the fractures just, oh, let's stop breaking the rock, right? They keep going. You're just not seeing them in the vegetation, right? So when you think about what does the surface of that aquifer look like, it looks like this everywhere, right? It's just how much stuff do we have on top of it. Okay, so that's the vertical fractures in the Silurian dolomite. These are the bedding plane fractures, and this is an odd picture if you're not used to looking at bird's eye. Has anyone ever seen a bird's eye camera where it gives you like that 360 view? So take a bird's eye camera and lower it down a well. That's what this is, right? So you've got a 300, this is going down basically a 3-inch hole in the rock, and that is a bedding plane fracture coming into that well and moving a lot of water, right? So it's the fracture network that really moves the water in this northeast Wisconsin karst system. Actually, in most karst systems, it's the fracture network that's really moving a lot of the water. Okay, so that was a brief introduction to your two karst areas. We're going to take a little pause now and think about the water cycle before we come back to water quality. Okay, so water cycle. Yeah, I love the water cycle. Everyone knows the water cycle, right? So it's easy. Groundwater 101 and groundwater recharge. So we all know the water cycle. It's precipitating just, was it yesterday? Monday, when it snowed all day, right? That's precipitation. We're good for it. Right, so water comes out of the atmosphere as precipitation, rain or snow. Right now, we're storing that precipitation on the ground surface, but eventually it's going to infiltrate, or it's going to melt and run off to surface water. Right? All the water on the planet, like, it just keeps cycling through the water cycle. The groundwater that infiltrates, a lot of what you get at a well, like especially a private well, is infiltrating pretty close to that well and moving to that well. And we're going to talk about that process of infiltration and also the process of groundwater recharge. Is that a word that people have heard before? Okay, so we're going to focus on, we're not going to worry about all these other parts of the water cycle. We're just going to worry about infiltration and recharge. Okay, but first, what's groundwater? It's the water that's filling the pores, cracks, fractures, and holes in geologic material. So since it's a cold night, imagine a beach again, right? A nice sandy beach, and you're sipping your favorite beverage, and it spills. What's it do? It goes in the sand. There's no underground river. There's no underground stream. It's just little tiny holes in the sand that the water soaks into. We call those pores. That's the fancy word for holes between grains. In the dolomite, it's the fractures, but it's the pores and fractures that the water is moving through. Why do we care? Well, we care because in Wisconsin, about 70% of us drink groundwater. Right? It is the water supply for the vast majority of the residents of the state. If you live along the eastern coast of Wisconsin, Milwaukee, I grew up in Cudahy, right? Those cities, we use Lake Michigan water. Actually, Oshkosh uses Lake Winnebago water. No. It's treated, come on. But so a couple cities use surface water supplies, but most of the state, including Madison, uses a groundwater supply for their public water supply. And okay, groundwater's under your feet. It's hard to have a good picture. There you go. Groundwater flowing out of a well. Okay, so let's think about different parts of, how many people have heard the word water table? Many. Okay, so above the water table, you've got all those little pores, and some of them have air in them, and some of them have water in them. And a lot of times if you dig a hole in your yard, it might be moist, the soil might be moist, but that hole isn't going to fill up with water because it's not saturated with water. You're in the unsaturated zone. The pores have both air and water in there. Once you pass that water table, then you are saturated. Your pores are full up with water or saturated with water. And if you dig a hole down there, i.e. a well, it will fill up with water. Okay, so that's the unsaturated zone and the saturated zone. Now thinking back to that infiltration idea, water infiltrates into the ground, but not all of that infiltration is going to make it to groundwater recharge. And think about seasonality of the water cycle. So in the summer, we get rain, right? But we also have growing things, green stuff. Kind of missing the green stuff right now. But you've got crops and you've got trees, and the water that gets into the soil zone is pretty quickly transpired back out by plants. I mean, a corn crop or something, it wants an inch of rain a week. We typically get 3 to 4 inches a month. So that just meets plant needs, right? So that's not going in, right? So the times where we get groundwater recharge, it has to be times where that water seeps past the root zone and actually gets into the saturated zone. And the next slide will look at sort of the seasonality of that, when that happens. Okay, then, so when we think about, well, how do I know that water's actually getting into my aquifer, getting down here to the groundwater system? Well, there's some obvious stuff like the water level in the well goes up. Okay, that's good. Or there's changes in chemistry that can tell you that water, a different chemistry is coming into the system. Okay, so this is seasonality of recharge, and this is some work I did up in northeast Wisconsin, I don't know, maybe a decade or so ago. There's 4 wells, one in Brown County that's yellow, one in Kewaunee County that's red, one in Calumet County that's blue, and one in Manitowoc County that's green. Right, so these are water level measurements from 4 wells for about a year, September 07 to August of 08. These are basically measured with something called a pressure transducer that you can lower down a well and just record continuously. So I was taking measurements every 30 minutes to see how the water level was changing. In terms of how much sediment was on top of the aquifer at these locations, it was anywhere from 7 to 18 feet. And when does recharge happen? Well, here's a nice water level rise, right? In 3 out of 4 wells, there's a nice big rain event. In the fall of the year, once your crops die back and your trees lose their leaves, if you have a wet fall, you get groundwater recharge because the plants aren't taking it, right? So it goes in. If you have melt events in the winter, here's a little melt event in December, here's a little melt event in January, right? And this one, all the water levels and all the wells go up. Here's the snow melt event in March. That's our major recharge period normally. So when that big snowpack outside decides it's time to go, some of it's going to run off, but a lot of it's going to go in, right? So that's a big recharge period. And then, does anybody remember summer of 08? I lived in Oshkosh. We got 13 inches of rain in like 4 days. I was actually at a conference driving home from the Dakotas, and the city of Oshkosh, I was driving across the central sand plains. It's all sand. I was following the storm. There was standing water in the fields. I'm thinking, oh no, this is not good. These are the kind of things hydrogeologists think about when we drive. If there's standing water in the sand plains, this is one big storm. I get to Oshkosh and like all these intersections are flooded, so I'm wending my way through the city to get home. And then my brother the next day my brother lives in England, he sent me a picture from the internet of people canoeing in the intersection by my house. That was the summer of 08. We don't normally have summer recharge. This is June of 08. We had summer recharge. So sometimes we get summer recharge, not very often. Okay, but think about this when you think about vulnerability of karst landscapes. Think about typical cropping systems. When do we put stuff out on the fields? Well, after we take the crops off, we usually spread a load of manure because we got to get the pits down before winter, right? So we're putting stuff out in fall, right? And then in the spring, after snow melts, before you plant your crop, we put stuff out. So where are you in this spring recharge event when you're doing that? So the timing of our cropping systems is not always working hand in hand with the timing of our hydrologic events. Okay, so that was your brief intro to groundwater there. I can do that in 2 semesters at Oshkosh anyway. So why worry about karst? Well, there's the obvious one, like if that opened in your road, it would be bad. Okay, so collapse is a bad thing. If you have something built on top of it, it's not a huge deal in a farm field unless you're driving your tractor across it when it goes. But anyway, so collapse is not something great, but also groundwater vulnerability. This is the C&M sinkhole up near Sturgeon Bay. Here's a road culvert, all the water comes under, goes in, and boof, down that sinkhole. Right? They become focus places of infiltration. So let's think a little more about groundwater vulnerability and what makes an aquifer vulnerable. I apologize for this map. I didn't make it, especially if you're red-green colorblind, because it's really not going to work for you. But red are vulnerable areas, green not so vulnerable. Big, thick clays. And then there are lots of vulnerable areas in the state, right? So vulnerability doesn't necessarily mean contamination. It means potential for contamination. The things used to generate this map are the type of bedrock, depth to bedrock, depth to water table. Is it 5 feet? Is it 50 feet? Is it 100 feet? Soil characteristics, and then characteristics of superficial sediment. Okay, so Northeast Wisconsin, you've been hearing about it a lot lately with Kewaunee and other things, but this is not new, right? I got this from Ken Bradbury, who was one of my advisors for my master. This is a 1981 article. Door County sitting on fragile groundwater supply. Poisoned water, a nightmare for Fond du Lac area farmer. This is the early 1980s. I can actually find one from 1959 about a brown water event. And this has been historically a problem. How many people have heard of brown water events? A few. We'll see a picture in just a moment. It's not pleasant. I got this from Gordon Stevenson, who used to be with DNR. So this is basically from 2000 till 2005, the number of wells that had brown water events. And by brown water events, I mean actual manure coming into someone's tap from their well. Okay, so Door County, 05, 2 wells, Kewaunee, Brown County, Manitowoc, Calumet, Green Lake, Dodge. But let's look at where those are. Oh, looky, areas of thin soils, over Silurian dolomite, right? That's brown water. Yeah, so this is from Davina Bones in Kewaunee County. This is an October 2016 rainfall event. And we're actually going to look at some other data from some other wells at that same time period. Now, when we have one of these events, this well, one well turned brown, and obviously no one is going to drink water that comes out of the tap that looks like this and smells like manure. But there'll be a number of other wells in the area that might have bacterial detections or other things that don't visibly turn brown. And so these events are concerning primarily from public health perspectives, because I mean, that is raw manure in that person's water. Okay, so let's think about soils. Most people don't, but we are going to. So we'll just define them first. What do we want? Think about what we want soils to do, and how does that relate to vulnerability? Soils, dirt. Don't go outside and get dirty, right? Play in the dirt. Okay, this is a slide from my intro class. That's what we call the dirt outside. Common name for loose, broken down fragments at the Earth's surface. Of course, scientists have to call it fancier things. So this is just a slide from an intro geology book. Here's your rock, your bedrock, and then you have loose material on top of it. And that loose material, it can vary in thickness from almost nothing to hundreds of feet, right? And that's true in Wisconsin. The loose material over our bedrock is typically glacial sediments, either glacial till or outwash or a variety of other sediments coming from the glaciers. Now, to an engineer, they will call this whole package soil. Basically, if you can dig it and don't have to blast it, to an engineer, like a civil engineer, that's soil. Okay, so when you hear about soil thickness, people are actually talking about different things. Engineered means I don't have to get the dynamite out. I can dig it. That's not what a soil scientist or a geologist means. For a soil scientist or a geologist, we're really talking about this. Everybody seen like a soil profile at some point? Or seen one, heard of one? The A horizon, your nice topsoil. The B horizon, which is often your rooting zone and has some developmental, you can see layers where soil forming processes have happened. When we talk about this kind of soil, which is what the Natural Resource Conservation Service is, used to be the Soil Conservation Service, part of USDA, we're really just talking about the top 4 to 5 feet, where there's actual evidence of soil forming processes. And when you get down to the bottom, you're in the sea horizon, and then below that is just parent material. So it depends on what you're, like I said, there's a lot of different words, and you'll hear it used different ways. So to a soil scientist, it's a mixture of mineral matter and organic matter where you can grow plants. Okay, so now let's think about what we want soils to do. This is the DNR's land use and groundwater picture. It's been around forever, right? Here you've got a lot of glacial sediment. Now you can call that soils or not, right? But we've got septic systems, right? We've got a livestock lagoon. We've got a farm field here, right? We've got road salt. We have underground storage tanks, right? We have urban areas with runoff. We may have mining. There's a lot of things happening at that ground surface that you don't want to drink. You don't want to drink any of those things, do you? No. So this is what we want soils to do. We want soils to hold nutrients in the root zone for those plants that we want to grow. We want soils to filter microbes, viruses and bacteria, out of recharging water. And the kind of recharging water that might have microbes would be like septic drain fields. We land apply sewage sludge. We land apply livestock manure. Those are good sources of nutrients for plants, but you don't want it going in your well. You don't want that brown water, right? We want soils to retard the movement of certain chemical contaminants or assist with the breakdown of things like petroleum products, right, that run off the road, or pesticides. So you're asking that, however thick that thing is, it's got a lot of work to do, right? So soil thickness. If you don't have much, it's a problem. So this is, the Department of Natural Resources just changed the rules about where and where you can apply waste over the Silurian dolomite aquifer. So in areas with less than 20 feet of sediment on top of the aquifer, there are now some restrictions, right? So this is Marv Sherrell's map from the 1970s. Some counties have done more detailed work, but this is the general map. And then in these blue areas, these are the areas where you have less than 20 feet of superficial sediment, i.e. soil, on top of that rock, right? The other thing that matters is, what are those soils like? Are they sandy, right? Because sand's going to let water through more easily than clay, right? So the characteristics of those soils matter. So areas with thin soils and coarse textured soils, in general, they're going to be more vulnerable to contamination. So I'm going to take a brief diversion, then we're going to look at some of this well data from the Northeast. This is a great resource. I can't imagine how many times a week I go to this thing, right? UW Stevens Point put it together, the Center for Watershed Science. They've been doing homeowner testing programs for decades, and those are all in a database, and they're fuzzed out to the square mile. So you can't match it to a specific well, but you can kind of get a sense of where it is in relation to the geology. And you can look at it at different scales. I just Google it, right? Stevens Point Well Water Data Viewer, and it takes you to this page. It's an interactive program that lets you look at groundwater quality data at a bunch of different scales. And for example, this is at a county scale. You're aggregating results to the county scale, and it's showing you the percent of wells that were positive for bacteria. Wells aren't supposed to have bacteria in them. It's supposed to be 0. Anything in red is greater than 25%. That's not a good thing. Okay, so these are some data from a while ago. This is from the Northeast Wisconsin Karst Task Force report. So like I said, people have been thinking about this for a long time. Underneath the map is that vulnerability map. Over here, we're looking at bacteria in Northeast Wisconsin. Over here, we're looking at nitrate. So let's look at bacteria first. These kind of gray dots don't have bacteria. Black dots, one or more wells in that town or in that square mile had bacteria. And looky, this is not random. Let's look at Calumet, Brown, part to Brown, part to Kewaunee. All the areas where it's sort of mapped to be vulnerable, that's where you have bacteria, because that's where you have thin soils. It's even tighter with nitrate. Okay? The drinking water standard for nitrate is 10 parts per million, so there's kind of gray dots, kind of blue dots, and kind of black dots. They're kind of merging together in here. But again, look, where it's vulnerable in Calumet, a lot of black dots. Where it's vulnerable, lots of black dots, lots of black dots. So the things that we think are going to lead to vulnerability, thin soils over fractured rock, indeed do lead to vulnerability over those areas. Here's just zooming into one county. I got these from the Calumet County Land and Water Conservation Department. Daniel Santry is their groundwater education specialist. Here's an area of thin, loamy soils. Loamy soils are sometimes called light texture soils, a good mix of sand and silt and clay, like not too coarse. It'll hold water for your crops, but not too clayey. It's not too, like it doesn't bog down your fields, your tractor in your field. These are very clayey soils and much thicker. Again, now let's look at nitrate. Blue means less than 2, white is 5 to 10, red is greater than 10, and black is greater than 20. There's some clumping here. Okay, that's nitrate data. Throw the E. coli data on top. E. coli are these big yellow things with X's in it, all clumping over here. It's not all of Calumet County has problems. This part of Calumet County has problems, right? So they've done lots of water quality sampling. A lot of these counties in northeast Wisconsin have. If they look countywide, it's about a 32% unsafe rate, which is not great, right? And that's either because of bacteria or nitrate. And this is what that breakdown is. Total coliform, which is everywhere. E. coli, which is fecal, and nitrate, those are your percents. Now, if you contrast that with the karst areas with thin soils over the dolomite, 43% unsafe, 25% for total bacteria, 5% for E. coli, 28% for high nitrate. So yeah, you're getting a theme here, right? Thin soils over fractured rock lead to very vulnerable conditions. So now let's think a little more about that soil. This is down in Dodge County. It's kind of a little siltier soil, a little heavier textured. This is a tile line. With heavier textured soils, we often put in tile drainage systems to help drain those fields so farmers can get in and work them. So that's maybe, I don't know, what, 4 feet down or so? This is a guy from, I think he's from Ohio. I was not there at this field day, but he's lighting a little smoke bomb, and he's going to throw it in this thing and pump the smoke down into that tile line. These are photos from Fred Madison, who's a soil scientist that I used to work with at the State Survey. And when he does that, that's what you see. This smoke is coming up through that much soil pretty much instantaneously, right? And you're thinking, wait, this is heavy texture. This is like silts and clays. How's it doing this, right? Stuff's supposed to move slow through that. That's why we have a tile drainage line there. It's called macropores. Right? These are worm burrows. Right? And if you are in a clayey or silty soil, think about, like, have you ever played with modeling clay, Play-Doh? You make a hole in it, and it stays there, right? Take a thing of sand, make a hole in it, it all just slumps back in. In those tighter soils, when you make a hole, like a worm burrow or a fracture, it will stay open, right? And if you have these fractures and worm burrows and things, they can go down pretty far. This particular picture is from an area where they did a backhoe pit because there had been a field and there was like a February melt and all the manure ran down to one corner, sat there for like about a day, and then suddenly went away. And then like the next day, 6 wells turned brown. It went through 15 feet of clay. So when you're thinking, oh, it's clay, it's protective. Now you've got macropores. Okay, so that was like more about soils than you probably ever thought you'd want to know. So now we're going to look quickly at recharge and water quality. We're going to focus on the Kewaunee County groundwater study because that one's done, and I know more about the Northeast, and we'll very briefly talk about the Southwest before ending. So the Kewaunee County study, there were lots of us working on it. So there's me, I was at Oshkosh at the time, Mark Borchardt and Sue Spencer, who are up at the USDA Agricultural Research Station in Marshfield. Randy Hunt, who's another hydrogeologist with the USGS. Dave Owens is a hydro. Joel and Aaron work with Mark up in Marshfield. Davina was the county conservationist. And Bernie is a statistician who did some of the statistical work, which actually I'm not going to talk about much today. What were we trying to do in Kewaunee County? We were curious as to what is... The Stevens Point data are great, but a lot of people argue, well, that's only homeowners who know they have problems who submit samples. You don't really know if that's representative of all the wells in a county, right? What if it's just people who think they have a problem, so that's why they get their well tested? So that was one of the things we wanted to see, like what really is the contamination rate in Kewaunee County in a randomized sampling as opposed to homeowner volunteered sampling. So that was the first objective. The second objective was, once you had some wells with problems, right, where are those problems coming from? Where's the E. coli, where's particularly the fecal matter coming from? Is it coming from people or is it coming from bovine, right? And not to be blunt, but when you excrete, you have certain viruses in your gut, and the viruses in your gut are not the same as the viruses in a cow's gut or bacteria or other things. And when you excrete that, it goes out with that, right? So you can sample groundwater for those fecal indicators and tell whose poop it is, bluntly. And then one of the things, this is the question that I really wanted to know about is, what is the peak transport of viruses? Whenever we've had one of these brown water events, not whenever, but often, somebody will say, oh, I was drinking the water yesterday, it was fine, but now they're very ill, right? And the next day the water turns brown. So if you think about breakthrough of a contaminant like a bell curve, right? You have the front end stuff, you have the center of mass, and you have kind of the tail. What if the brown comes through in the middle, but the viruses start coming through over here, right? That's what I wanted to know. Which didn't quite work out the way I wanted, but we'll get there. So, objective 1. This was the countywide randomized sampling of private wells. Now, we knew that depth to bedrock was going to be an important variable, and so it was stratified based on that. So we took an equal number of samples from the 0 to 5 foot bedrock area, 5 to 20, and greater than 20. And so the red areas, these are the less than 5 feet. This is 5 to 20. These are parcels that have septic systems. That's sort of how we randomized. You don't want to try to sample a farm field when you're doing the random pick. We had great participation. People were very interested in the study, and you send out 800 letters to get 400 samples, and it was easy. We did synoptic sampling, which means we would send a letter out to people with a sampling kit, and we would say, okay, between Friday and Sunday, we want you to sample your well and bring it to these collection points. So we're collecting them sort of all in a short time frame, which, like, those of us on the study can't go get 400 samples in that kind of time frame, right? So we're using homeowners to do the sampling and just bring the samples to us. Because recharge plays an important role in water quality, we sampled once during a recharge period, which was November of 2015, and then once during a non-recharge period was the following summer. Okay, so what did we see? In the areas of very shallow soil, during recharge periods, half the wells had problems. Either you could have any one sort of a smorgasbord. You could have high total coliform or high E. coli or high nitrate or all of the above for percent positive wells. So half the wells had problems, not so much during the non-recharge period. With the 5 to 20, a lot of this was actually nitrate, and there wasn't a big difference between recharge and not recharge. But once you get past 20 feet to rock, the water quality starts improving pretty nicely, which is encouraging. Objective 2. Determine source of fecal material. So this is Mark Borchardt, this is Sue Spencer, who were that part of the study. These are some Kewaunee County residents. We use hemodialysis filters, right? If anyone has a friend who does hemodialysis, it's little tiny tubes, right? So if you run water through little tiny tubes, it will catch little tiny particles like bacteria and viruses and things like that. So we run about 800 liters, about 200 gallons through this thing, and then we cap both ends and mail it to Mark's lab. That's what I do. I'm the groundwater person. So what we did is we took wells, of the wells that had problems. If you're looking for source of fecal contamination, you don't want to sample a clean well. So of the wells that already we knew had problems, those are the ones we sampled for source tracking. We did 5 rounds of samples, and each sampling round consisted of 5 to 30 wells that were sampled. And we did it in April, right, as people started to spread manure. We did it in August, early fall, October, November, January during a winter melt event, and then March during the big spring recharge event. And these are our results. Okay, so this is the water level over time. So remember, when water levels go up, you're in groundwater recharge periods. This is April, and then pretty much from April till fall that year, we generally had falling water levels. And then we had a very warm, wet winter that year. So starting in September, we had sort of these continuous punctuated recharge events all the way through till the following spring. Okay, so what did we see? The first round of sampling, people are just starting to spread their spring manure, but we're not in a recharge period. And of the samples we took about 25 or 30 samples, about 15 contained human detected viruses, about 5 bovine. The second round of samples, also no recharge, And humans are again pulling in the lead here with 6 human and 5 bovine results. Okay, now we come into fall of the year, crops are off, we've put our manure out, and bovines come charging into the lead. 1 human, 17 bovine in the November sampling event, right? We had a January melt event. Bovines again in the lead, 11-3 during a recharge event. We're starting to see a pattern here, but no. When we get to the March sampling event, humans once again take the lead, 9 humans, 6 bovine. And it could just be, you have to think about whether that source is out there. We put that manure out there in like October, so maybe we'd pretty much moved it all through by the time we get to the March sample. I'm not sure, right? But those are our results. So what do we think is happening? In rural areas, people have septic systems. Here, if you're in the city of Madison, you flush and it goes to a wastewater treatment plant. To a septic system, you have a tank which bluntly captures the larger particles, and then all of the liquid goes out to your drain field and infiltrates, which, the viruses aren't going to stick in the septic tank, right? They're going to go out, and the idea is that the soil will filter those out. That is the hope. So you have this slow, constant, steady drip of effluent from septic systems, and you're injecting it at least 3 feet down because you don't want that sucker to freeze in the winter, because you still need to be able to flush in the winter, right? So that's that constant but low-level source. In terms of bovines, we put it out occasionally. I forgot how many thousands, maybe like 3,000 septic systems. There's like 45,000 cows in. That's not the right number. I don't know the exact number of cows in Kewaunee County, but it's a lot of waste. We put it out periodically, and then we have episodic recharge events that push it in. And so it's a lot more variable. Okay, that was objective 2. Objective 3, this is the one I was interested in, sampling a homeowner well to see exactly when pathogens come through. But the problem with a homeowner well is they use water, right? So the water level in the well goes up and down like when they flush or do their laundry or do their dishes. And so if you want to use water levels as a way to indicate recharge, the homeowner well isn't going to do you, right? Because its water level is changing for other reasons. So we had 2 non-pumping monitoring wells. That one that you've already seen water levels from this one, KW183 was part of that study back in 07-08, so we reutilized that one. And then we put a new one in down here at the fish hatchery. So these are our monitoring wells. And these are shallow wells. This one is only 33 feet deep. It had about 7 feet of soil. That's that little brown bit there. And the casing, the pipe, just barely went into the top of the rock. At the fish hatchery, it was 46 feet deep. There was a little more soil here, about 11 and a half. And again, the casing is just into the top of the rock. Okay, so those are our non-pumping monitoring wells. And we measured water levels and water quality parameters like pH, fluid conductivity, dissolved organic matter. We measured lots of things in these wells. Okay, now on the homeowner well, we used the automated samplers. And this is a homeowner well up in northern Kewaunee County. The well is 303 feet deep. This is all to scale. His pipe goes down 200 feet. He only has 2 feet of soil, which you can probably barely see that brown line up there. And his water level was about 25 feet. Okay, so for us to see contamination in his well, it has to come way down and in for us to see it. Okay, and then what we would do is we'd, again, send the samples, those hemodialysis filters, off to Mark's lab for quantitative polymerase chain reaction microbial sampling for the microbial targets. Basically, you're looking for the DNA of the microbes. This is what it looked like in the person's basement. These homeowners had to be exceedingly tolerant. When we were running this thing, I was probably, me or somebody from the county was probably popping into their basement every other day. Hi. Right? So here the water line comes in from outside. Like I said, this is the basement. This is their pressure tank, right? And then the water would come over into our sampler. If we weren't pulling a sampler, it would just sort of flow past and through this water quality sonde where it would record lots of water quality parameters, and then it would discharge down the floor drain and go away. If we wanted to start pulling one of the microbial samples, we'd open these valves and, filter 1, filter 2, filter 3, filter 4, we'd fill them all up. Here's a data logger. Dave Owens is a whiz, USGS is a whiz with data loggers, and he can program it to do, phone your mom on Mother's Day if you want, right? I mean, he can make them do anything. He's great. Right? So these are our results. These are the water levels. Okay, so from fall of 15 to spring of 17, recharge, not recharge, and then that very wet winter with episodic recharge. The same variation in water level at KW 183. This is the Fitch Hatchery well, which we drilled right here. They were pumping it in the fall to get water for the fishies. And so when they turn the pump off, the water levels go way up. But I mean, generally they match pretty well. These are the recharge periods, right, when you have rising water levels. And this is when we had the otter sampler running. So we were running it almost continually during recharge times. We're only going to look at one set of results. Okay, here's that monitoring well. And now we're looking at hourly precipitation. This is the rain event that produced brown water at that other lady's well. The rain starts at 8 in the morning, continues for about a day and a half. The water level rise in my shallow little monitoring well starts about 1 o'clock, so about 5 hours into the rain event. These are water quality parameters from this well, and we're going to focus on the colored dissolved organic matter, because organic matter is coming in from that top organic rich soil zone. So it drops and then it inflects up, right? And that inflection is about 6 hours into the rain event. And notice it peaks about 30 hours after the rain event peaks. So you're flushing in organic matter from the top of that soil column. Let's go see what we saw at the homeowner well. Remember, it's that very deep well. These were actually continuous samples. I just didn't know how to make the bars fat enough to show you that. But anyway, so what you see is, here's coliform bacteria, which again is coming from the ground surface. It peaks about 30 hours in, and then it drops back down. The viruses were very sporadic. They just sort of randomly showed up and not. So I didn't really get what I wanted to about the viruses and bacteria coming in. The total coliform gave a nice signal, but the other thing that was rather illuminating and scary is you're going from, we actually were measuring per 10 liters, so that's why you have sort of fractional amounts here. But it's varying over 2 orders of magnitude on the time frame of 16 to 18 hours. The water quality in this homeowner well is changing really rapidly, right? So from one day to the next, it can change because the groundwater flow system just moves that fast. Okay, so we're going to finish up northeast Wisconsin. Recharge is really rapid, and wells respond within a day or two to precipitation or melt events. Most of it comes in the spring. However, fall could be important and winter can be important depending on the winter, those weather conditions. The total coliform was wildly variable across that recharge event, which means the water quality in a domestic well can vary on the order of every day up there. And the recharge penetrated hundreds of feet into the saturated zone within 30 hours. Okay, so in the northeast, more deeply cased wells probably aren't going to help if you're still up in the Dolomite Aquifer. Now, this may be different in the southwest, which is where we're going to go next. But in the northeast, deeper wells don't get you better water, which is unfortunate because it'd be nice if there were a simple solution. Okay, I don't know nearly as much about southwest Wisconsin, Carson, so we're not going to talk about it for nearly as long. Right? We do know that there are water quality problems, right? So this is that bacteria map, right? So if you look at the county scale, about 25% of the sampled wells had bacteria problems. But then if you go down to the square mile scale, like there's not really a lot of data in Grant County, right? Or this is Iowa County, this is Lafayette County. There was some sparseness to the data there. The geology is actually really well known, right? We used to mine southwest Wisconsin. It's the tri-state lead zinc mining district. So south of 151, there are very detailed geologic maps all the way through here and into Iowa and into northern Illinois because we mapped it to try to find the metallic mineral resources. The groundwater flow system doesn't work the same way as in northeast Wisconsin, at least as far as we've figured out so far. But recharge, again, appears to be pretty rapid. Okay, so just to kind of a quick, we've been talking about this, the Niagara Dolomite Aquifer. Underneath that is like a 200-foot thick shale layer that water doesn't get through very well. This is missing in southwestern Wisconsin. So our uppermost rock is this galena. And a lot of people have wells in the galena. Under this top package of rock is the St. Peter sandstone. Some people have their domestic wells in that. And even deeper is this Cambrian age sandstone, and actually a lot of the deep municipal wells like Madison's are in that. So there's a lot more variability, and you can be drawing water from different rock layers. Up here, we were always in the eastern Dolomite Aquifer. Okay, so there's different rock types. The uppermost rock that you see a lot in southwest Wisconsin is this Galena dolomite. If you're driving down 151, that's probably what you're looking at. And see, it's got all these little vuggy holes in it, right? Underneath that, there's a limestone. This is the Decorah Formation. And then there's the Specs Ferry, which is a shale, which does not move water very good. Then you come into the Platteville, which is sort of a mix of some dolomites and some shales. So you've got a nice aquifer, and then some possible kind of shaly layers in there that won't move water very well. Okay, so underneath that top unit, you have this Ansell group that consists of the Glenwood Shale and the St. Peter Sandstone. This is a good aquifer that a lot of people use. Underneath that, you got more dolomites. Okay, now, the Prairie du Chien dolomites were deposited in the ocean, and then sea level fell. And that rock layer was karstified way back in the Ordovician. So if you ever wondered why, I'm sure you've all looked at the stratigraphic column for Wisconsin. If you've ever wondered, like, why does that sandstone go way down like that? Well, because we karstified this surface before we put the St. Peter on top of it. And so in some places, it's not karstified at all, and the St. Peter's thin. In other places, it's way karstified, and you fill it all in with St. Peter. Right? So it's just like the modern landscape is not flat, right? There's hills and valleys. You karstify and erode the top of the Prairie du Chien before you lay this whole package of rocks on top of it. And so when that unit is at the top, it's quite karstified because it's got this round of karst plus the one that it had from back in the Ordovician, right? Okay, so let's look at the geology real quick. This is a 151 road cut, right? Look at that. I mean, this is telling you where the water's moving. And in the winter, it's even better because it freezes and the icicles are there. Right? So what are we looking at? This is the Galena. Right on top of the Decorah, that's that seepage layer. Right? Water comes down, and then it goes sideways. Because that Decorah has shales in it. Madeline Gockwitz, who had this job before I did, also found another kind of neat thing about this aquifer system. I just showed you the Decorah, which is a shale. The Glenwood is also a shale. This is some work she and a graduate student did near Governor Dodge State Park, where they actually have two separate flow systems. The upper flow system consists of the Galena and the Platteville, and it perches on the Glenwood. And then there is an unsaturated zone. And then the St. Peter and the Prairie du Chien are a lower aquifer. We don't have that in Northeast, right? So this is sort of a more complex flow system because the geology is more complex. So what do we know about the Southwest? And again, I've worked in the Northeast for 30 years. I've worked here for less than a year, so we gotta give me a break here. The topography is really different, right? It wasn't glaciated. There's a lot more hills and valleys. So in Northeast Wisconsin, you have a high area and then flow all the way over to Lake Michigan, all the way over to Green Bay. Here, you've got hills and valleys with little streams in between. So you have short little flow systems from ridgetop to the adjacent creek. Because the actual rock layers are really different and variable, you can get a lot of lateral flow. Here's Madeline's little conceptual model, and notice right on top of this perching layer, there's a spring. There are springs all over southwest Wisconsin. This is the State Survey's spring database. Notice we don't really have very many in the Northeast, right? It's just a different animal. It's a different type of karst. We do have some preliminary hydro. I just want to show you some water levels. George Kraft, he's retired from Stevens Point. He put in a bunch of wells at the UW Platteville's Pioneer Farm. Okay, so these have been in for 14 years now. 13 wells, 6-inch well. And within it, there'll be 2 or 3 little 1-inch wells completed at different depths. And then there's a pressure transducer sitting down it that records water levels. So we're going to look at some of those. Here's the farm. Here's the top of the hill. Here's a well right there. Ooh, I had this animated. Ridgetop. We're going to look at water levels from that well. Halfway down the slope, toe of the slope, and right next to the stream. And these are all in the next picture, right? So we're just going down the hill here, looking at water levels in these wells. I just found these. This was awesome. I went out to go see what the monitoring system was like, and somebody left those level loggers in there. They've been sitting there, I think, since 2013 when somebody last looked at them. So I pulled them out, and I called George. He's like, I don't think they're mine. Ask everybody at the farm, ask everybody at Platteville. Nobody knew what they were. I mailed them off to Canada. They downloaded the data, put new batteries in them, and I'm good to go. It's awesome. So I started on this project in June of 19. I got data from January of 10 to November of 17. And the only reason I wanted to show it is you should recognize this pattern, right? These are really spiky recharge events in response to rain. So I think that really rapid recharge and spikiness and getting in fast, I think that's going to carry across, but I'm not positive yet. That was 7 years. It's kind of hard to see anything, right? So let's just look at a big summer rain event. Here's the wells down by the creek. Here's the ones halfway up the hill. Here's the ones way on the top of the ridge. They're all responding to that event, like within a day or two. So that seems consistent. Okay. What are we doing down there? We're basically doing the Kewaunee study all over again. Right? So the SWIG study is the Southwest Wisconsin Geology and Groundwater Study. It is Grant County, Iowa County, Lafayette County. It was initiated and sort of funded by the counties. It's the state survey and also Mark Borchart's lab up in Marshfield. The study design is strikingly similar to Kewaunee. So random selection of a bunch of homeowner wells, right? Do it twice. Once you know which wells have problems, randomly select from that to determine fecal source. We've done 3 rounds of fecal sampling. I think the results for the first 2 have been released. We haven't done the 4th. This one is still being analyzed, and the 4th one hasn't happened yet. So we're again looking at human pathogens, bovine fecal markers, but we're adding pigs in because there's more pigs down there. So that we're kind of in the middle of that, right? So 2 synoptogrounds of samples, 4 rounds of fecal source sampling in the middle of it right now. Geology matters, right? The depth of bedrock and type of bedrock are going to matter. We don't have glacial materials down here. When you weather the dolomite, you produce a unit called the Roundtree Formation that is a clay weathering product. Exactly where that is and how thick it is not well known at this point. So corollary to the SWIG project is a project at the survey that we call the Roundtree Formation Project, where we're mapping the thickness and extent of that unit to try to see if it's protective of groundwater. And then we're also making depth to bedrock, water table, and bedrock geologic maps for Grant County. Iowa County already has some, and there's not enough time to do all 3. Well they might matter. Like I told you, it doesn't matter in Northeast. It may very well matter in the Southwest. This is what Minnesota does. They have different names for their rock layers, even though they're exactly the same on both sides of the river. This is their Galena, right? And then there's the Decorah Shale, the Platteville and Glenwood, and then the St. Peter. These upper layers, they tend to have really high nitrate and really recent water. Below the Decorah Shale, it's older, tends to have a little better water quality. You can use things to date groundwater, which we're not really talking about today. Minnesota doesn't allow you to connect across that Decorah Shale. We have no such well construction codes in the Southwest, and that may actually be important. If this aquifer is much more impacted by surface activities, you really don't want to punch a hole and take it down to the bottom one. That may be an issue here. Okay, so these are your things, right? Bedrock geology, water cycle, soils, land use. Your takeaways: karst is a landscape that forms by dissolving rocks. And because water is making the pathways and making those holes, it means you have a well-integrated network. And so water can move through it very quickly. It's like a positive feedback process. Soils are our protective cover. And if you don't have much, it's vulnerable. Or if you got macropores popping through it, that is also very vulnerable. Recharge is how stuff gets in, and it's not uniform. It varies seasonally, right? During recharge periods, what we're doing on that land surface, it really, really matters. And land use activities can easily get in karst settings, no matter what that land use is, whether it's an urban setting or an agricultural setting or whatever. Okay, that is the last slide. Does anyone have any questions? Yeah.
So, what can these homeowners do with this water? I mean, should they, is there boil it, or I mean, what are they?
So, I mean, in Northeast?
Yeah, just take your look at, I mean,
A lot of people.
without being brown, right?
Yeah, so he's asking what can people do to protect themselves if they have a private well in northeast Wisconsin. I had a friend from Oshkosh who moved up there, and he has small grandkids, and he called me and said, what should I do? And I said, there are ways, you can get disinfection systems that aren't that pricey, like a UV light that will disinfect it. Because, I mean, your primary concern is things like drinking pathogens that come with fecal matter. Right? And a UV light will take care of that. And so when the water comes from the tank, there's a transparent part of the pipe with a UV light shining on it that will disinfect. And so a lot of people are going with home treatment systems. The concern is people who can't afford that, right? That's always a risk. But, I mean, a lot of people treat. There's a lot of people who don't drink their water. They get those big carboys and they use that for cooking and drinking, and then, bathing and laundry, and you don't need to be pathogen-free for your laundry. Right, as long as it's clean water. Right? Well, the brown, nobody's going to go with the brown, right? But I mean, if it's, flushing your toilet, all that stuff. I mean, I don't know if you've ever gone to, I used to take students to Belize, and when you're on a tropical island off the coast, you flush with seawater, right? It doesn't have to be potable water for flushing and stuff like that. So that's how people get around it. They either buy or they treat. Yes?
How can they change the protective cover, the soil treatment, to increase the filtration activities in the soil?
So she's asking how you can make that protective cover be more protective, the soil layer. You can't really do anything. You can't truck in more soil. That's what you can try to do, and this is some of what they do when they apply, is if you inject and maybe plow, you can break up some of those macropores. So hopefully the nutrients, the manure is a good nutrient source, right? So you want to kind of keep it up in the soil zone. So if you can, do some injection and tilling so that it stays in that soil zone, that's good. If you can put it out there at different times, if we could expand out that window, that would really help. Some people are trying to do low disturbance side injectors so that when you already have corn on a field, you can do manure injection then, as opposed to having to get it on either before or after the crop, because then it's just sitting there waiting to go in, right? So timing of when we apply is another thing that people are trying to work around. Applying more frequently at lower rates. When I say manure, you tend to think like cow pies, but we actually have, manure slurries are like, a few percent, 2-3% solid matter, which I don't really want to think about it too much, but so that's kind of what we're putting out there. So it's a very liquid product. So if you could do some dewatering, that would help as well. If it were more solid matter on the being applied and injected and incorporated in, that would help because you're not pushing it through.
Would changing the organic matter level contact with the soil make a difference?
That is something that people are hoping for. The catch term for that right now is soil health. Having cover crops and incorporating those in and trying to build up the organic matter in that soil, hopefully that will hold at least the nutrients a little better. I'm not sure how it'll
Affect the bacteria.
Right. That's not known. We haven't really done any projects on that. Yes?
So I'm a geology student here, senior studying hydrology. And
Yay.
I think Lisa Haas here has used similar data about studying it, but my question is, what kind of modeling exactly have you done? I can think of these reactions can we think of these reactions as fast and reversible? In that case, do we know the retardation coefficient? And to protect certain homeowners specifically, can we do spatial moment analysis to make sure, to say, oh, your house specifically won't see the effects, especially in those cases where at the beginning of the plume, the water is clear, but there's still E. coli in it.
Yeah, so the problem is he's asking about a modeling approach to look at the water quality issue. We have not really done a modeling approach. A totally different piece of work that I haven't talked about was my PhD stuff, which was tracer tests and fractured rock, and monitoring those and then trying to model it. Any kind of porous media model is going to be completely inadequate to do this. You have to move to, just because it can't get the fracture network pathways. And in terms of the chemical modeling of it, most of those models assume equilibrium, and we're not, when you're going through macropores, you're not approaching equilibrium processes at all, right? So
The more heterogeneous systems
Yeah.
don't work. Correct?
So it's very hard to do numerical modeling on the system because some of the assumptions you make that the contaminant will have time to contact the aquifer materials and undergo reactions, that's not true. Right? It's just moving too quickly. In this system, stuff moves hundreds of feet per day on a tiny fracture surface, right, where you don't have a lot of aquifer surface area on which to perform reactions. And you don't really have the stuff you need. Like you need organic matter and other things to do it, and you're looking at bare rock.
So even like a Langmuir modeling system would be too slow, even though it's supposed to be meant for a fast system.
And what's it going to absorb onto? Another thing, right? In the back.
I wonder if you're followed up on your virus hypothesis, look at the Brownian motion of the virus, and,
Well,
what kind of detection systems did you use for the viruses, and what were the latency of that?
So he's asking about viruses and what we used for detection systems. The detection system was just the qPCR, like do you have a fragment of virus DNA in the system? We were not testing for viability at all, right? So the reason I think, are you referring to the auto sampler work where I was looking for them and I didn't really see them?
You thought that it was going to be before you saw them.
Right. The problem was in that, and I didn't say it, everyone in the county knew exactly where the auto samplers were, and no one spread any manure within 2 miles of them. So I didn't have a source term, so I never really saw anything. I saw coliform bacteria because I didn't have a virus. I didn't have a source term for bovine bacteria and viruses because everyone knew where they were.
So you need to put a test site in every
I'm thinking about things we can do at Pioneer Farm, where I can maybe try this again, because I didn't control the land use around we just sort of figured manure was being applied everywhere in the area and we would detect it, but nobody applied close to where I had my auto samplers, which was unfortunate because I basically never tested that hypothesis.
So on the one hand, you had this really excellent community participation with like 50% of people saying, yeah, we're in. But then on the other hand, you had people saying, okay, so there's all this sampling going on, let's hold back on our activity. So do you sense a lot of community pressure on farmers to clean up your act or change your ways, or you're to blame for my groundwater? And what's that community vibe like?
So she's asking about the community relations in sort of between the farmer and the ex-Burbia homeowner in Kewaunee County. And there has been a fair bit of tension. For the ex-Burbia homeowner, a lot of people live down in Green Bay, right? But you're surrounded by farmland. And the KW 183 well, USGS has put a webcam on it. People can go out, spread manure, and incorporate it in a day. So you leave in the morning, it's a brown field. You come home at night, it's a brown field. You don't even know that the field next to your house was spread, right? And then your well turns brown. So that creates one, ex-Burbia homeowners don't know farming cycles and so don't know times of vulnerability. Farmers are just trying to make a living cropping the land and having a dairy herd. And there's always been a lot of finger pointing, right? Like, oh, it's septic, oh, it's cows, oh, it's septic, oh, it's cows. At least what came out of the Kewaunee report is like, oh, what? It's everybody. Everybody's poops in the groundwater system. People poop, cow poop, it's all in there, right? And so it sort of moved past the finger pointing and sort of got to what can we start looking at for solutions in terms of can we not spread until after April? Can we use limited rates? And so I think that improved the relationships a little bit. There's a lot you're seeing around the state, not just in Kewaunee County, the growth of what are called producer-led groups. So in Kewaunee County, it's Peninsula Pride, and they're doing water sampling. And if somebody's well does have a water quality problem, they're providing like 6 months of clean water to that. So there's been some more coming together, looking for solutions rather than just pointing.
When I built a house in Door County in the mid-90s, they required everyone to have a holding tank. They seem to now be allowing people to have mound fields. sense to me considering that there's like this much soil.
Yeah, so he's asking about septic codes and how they may have changed from the mid-90s to now. There was a septic code change in about the year 2000, and I'm not remembering the number, it's COM whatever, that reduced the separation from your drain field. You have to have a separation to either water table or rock. And that used to be 3 feet, and that's now 18 inches. But if you have that lesser amount, there needs to be some pretreatment like green sand filters and other things to try to remove microbes a little better within the system. So there were some newer septic designs that led to that lessening of the separation distance from your drain field to rock or water. And that probably now gives people enough that they can get a mound in, right? Because you don't need quite as much as you needed to before. So that code change happened around 2000, and I'm just not remembering what the code change number was. COM 80? I don't know. Yeah.
I was astonished by the earthworm tunnels.
Yeah, shocking, isn't it? Yeah.
Yes, I mean, earthworms and shocking, who would have thought?
And do you know what else? Earthworms aren't native.
That was right there. So how does this, is this all new in the last 150 years then?
I think they thought okay, so repeating your question, you have a microphone. Anyway, I think they were thinking early settlers like 1700s brought earthworms in. I don't know if our native worms also make big burrows like that. I don't know.
But that's stunning because my one brother designs landfills. And the whole idea is, we're going to put clay down as a cap, quote unquote, and as a base. And nothing goes through clay except for these little damn earthworms. And your point that once they make the burrow, it's there for a long time.
Yeah, I have very silty soil in my yard, and I get desiccation cracks, right?
Yeah.
And you can just look at it and like, that goes about a good 2 foot down, right?
So that that was an amazing slice of biology in this whole thing. I'd love to hear more about that some other time, but that's really sobering to think it's going through feet of clay.
Yeah, actually, I think I presented a talk once to a group of sciencey people, and there was a soil person there, and I showed the brown water event, and then I showed the well construction report for the home well that was impacted, and it said 0 to 10 feet clay. And he called me the next day and said, well, that can't be right because it can't go through 10 feet of clay overnight. And I was like, but the well turned brown. Like, it did. Like, you're discounting the fact that macropores exist, right? I mean, it was still in his head, like, it can't go through 10 feet of clay. It's like, yes, it can.
Wow.
And it did.
How does artesian water fit into this, if at all?
Artesian water is, think of like the land surface, right? And water flows downhill. I purposely didn't put any, I thought this was too long already, so I didn't put any slides in about directions of groundwater flow. Now imagine, just take that land surface and make sort of a subdued surface, and that's the elevation of the water table. So if you think about a flow system, water is going to kind of go down a little bit here and go over and come up and out, right? And it's being driven by pressure. So if here's my lake level and I drive my pipe down to here, the pressure here is higher than the pressure at the ground surface, and the well will naturally flow. That's an artesian well. So the pressure down in the earth that the well screen is open to is higher than the pressure at the lake or in that flowing well, and so it flows up and out.
So if that water were tested, it would test the same way? Like water
Yes, indeed. Yeah. It's still the same. Sometimes people are like, oh, it's a flowing well, it must be pure. It's the same groundwater flow system. If you're in a car setting, be careful, whether it's artesian or not. Yeah.
Yeah, just a general question about how you measure the geological layers to create these maps. This is just like multiple cores, drilling cores, or?
So he's asking how we make geologic maps and things. So one of the great resources the state of Wisconsin has is that if people who live in the country and have a well drilled, well drillers have been required to submit well construction reports since 1937. Now, okay, they're not all 100% compliant, right? And they used to locate the well construction report to like the quarter section. So with the public land survey system, so the northeast quarter of the northeast corner, section 26, town whatever, range whatever, right? But we have those records. So you can look at that well construction report and say, okay, and I'm going to pick on Carol because I work there. It's like Carol McCartney owned the northeast corner then, and the log says Carol McCartney. So I'm putting dot on my map here, and I'm believing that log. And they'll say, they're drillers, they're not geologists. So they'll say like sand and gravel over blue rock, over yellow limestone, over yellow sandstone, whatever. It's not a geologist log. They don't put the formation names on it. But if you kind of know the area, you can then use that to not only get information about the rock layers, but also for me, they report the depth of water in the well. And so I can use that information to start making water table maps and things. So we use, the well construction reports are great, and there's thousands. I've been working in Grant County. There's, I don't know how many thousands in Grant County. A lot. So that's a great source of record.
Can you put a plug-in for the core depository?
Yeah, so we do. Okay, so we have these well construction reports, which are by drillers, but we also do drilled core as part of our research projects. Or if other people, like when the Crandon mine was a viable concern, they collected a lot of rock core to evaluate the mineral resources, and there are rock core available from some of the southwest mine areas. We have all that. We're the archival agency for the subsurface of the state of Wisconsin. And we have how many?
660,000 lineal feet of rock.
A lot of rock core.
660,000 lineal, you speak it into the microphone.
660,000 linear feet of rock core at a repository out in Mount Horeb. It's a big barn-type building, but there's some little rooms that are small, not heated, which, but there's some little rooms that are smaller and heated with good lighting where you can pull the boxes of rock core out and look at them and not freeze your fingers off this time of year.
It was pretty chilly out there today.
We had some school teachers out today.
Another question?
Oh, and I have to say this before we end, because Carol brought these for me. We have little karst information handouts from the Wisconsin Geological and Natural History Survey. Karst, avoid that sinking feeling. There's a picture of Jonathan Levy in a little sinkhole up in a roadside ditch in Door County. Information about karst, the figure I used, some stuff on the back, a map. They're on the side, on the back in both places.